Here we have an example. A sign of mass 20 kg hangs from the end of a rod of length 2 meters with a mass of 4 kg. A wire attached to the end of the rod and to a point 1 meter above point O. Find the tension in the wire and the force exerted by the wall. First step is to draw an FBD. Here we see the present forces, which are the force F with its components Fx and Fy. Fx is the force exerted by the wall onto the rod. We also have the tension T and its components Tx and Ty. We also have the weights W1 for the rod, which has a mass of 4 kg, and weight 2, which has a mass of 20 kg. In the second step we sum the forces along its rotation and axis. So for the tension we apply the second condition for equilibrium to solve it. So we examine the figure and determine if that force would cause rotation clockwise, counterclockwise, or no motion at all given the axis of rotation at the origin O. So for the first one is the force F, which is located on the axis of rotation, which we learn that it will not cause in rotation if its line of action intersects the point of rotation. The second term is due to the weight 1, and if we let the rod move freely this force will cause the body to rotate clockwise. The third is due to weight 2, which like weight 1 will cause the rod to rotate clockwise. And the fourth one is the tension T and will cause the body to rotate counterclockwise. Then we expand the equations and see that the angles between the lengths R1 and R2 with the weights 1 and 2 is the same, which is 90 degrees. The sine function of 90 degrees would yield a value of unity or 1. So we can simplify the equation for the tension as shown here. However, the angle theta is unknown and we need to find it first so that we can solve the value of t. To solve for the angle theta we simply examine the figure and we see that it can be solved using the lengths that are present in the problem. By applying tangent function we can obtain the value of theta. So, theta is the inverse of tangent of the ratio of 1 meter over 2 meters, which yields a value of theta close to 26.6 degrees. We then substitute this value to the expression we got earlier and we see that the tension experienced by the wire holding the rod in equilibrium is around 483.6 newtons. To determine the force exerted by the wall we use the first equation of equilibrium, which simply is the sum of forces along its axis. We see that the forces along x are just the force x component of the wall minus the tension x of wire. Upon substitution of the values of t and theta we get that the force x, or the force exerted by the wall on the rod, is around 432.4 newtons. Here we continue to solve the problem, which is not necessary but interesting to do since we can determine the force y by the wall. We can then solve for the force F of the wall, which is oriented as shown in the figure. It is around 432.8 newtons and oriented in a non-linear fashion.